for example, quite often you may want a marginal density. You may want to actually integrate out V or integrate out Y. And it turns out that integrating in a characteristic function, integrating out a variable, is like putting the frequency to 0. It's the same thing as that. So it turns out if you're wanting to get a marginal density, as you often do want, then it's equivalent to putting one or other of these things to 0. So in fact, the problem doesn't have the complexity that it looks like it has. Okay. Is there anything else I want to say? So what I've tried to describe is a general strategy by which people go about constructing these densities. You always go this way. If the problem happens to be strongly non-linear, you can still get to here, but you've got a little bit of a problem when it comes to actually calculating the cumulative function. It's just a little bit harder, that's all. Is there anything else I want to say here? Probably not. So what I've tried to do here, oh yes, one other thing which I want to say. Okay, one other important item. Probability density functions are very nice functions. They don't have the brittle properties of many of the functions you see. And the reason simply is they are essentially functions of complex intervals. So, think about this. Think, for example, the Gaussian distribution. I think Gaussian distribution. And this is the other situation that people play. If you take a look at Gaussian distribution, let's say. Once you go out several standard deviations, the Gaussian distribution, let's say 3 or 4 standard deviations, is 0 probability functions. So you may as well call the density here 0. So you may as well say, for example, if this Gaussian distribution is, let's say the mean value is u, and let's say that the standard deviation is sigma. If I go out to mu plus 5 sigma here, and mu minus 5 sigma, but the value here is minuscule. So I can expand this function as a Fourier series. I could write it as this function here. I can approximate this as the f hat of x equal to the sum from k equals minus n over 2 to n over 2 minus 1 of ak e to the ik omega x, omega, let's call it omega, and typically it would be something like omega over n, something like that. It's basically the Fourier modes. But it turns out that once you're in that framework, the AKs are, you can see right away when I reverse the Fourier series, the AKs are essentially they're actually Fourier integrals. They look like the following. They look like f hat of x. If you think about how you get the coefficient of Fourier series from the function, it looks like f hat of x e to the I omega, like x. They're like omega k, some omega x over L, something like this, integrated between. Well, in this case here, let me call that minus L, and well, in this case it would be something like